Okay, you two. Let's go back to the birth of the universe. Things are hot. Real hot. And things are happening fast. Real fast.
For the tiniest increment of time that is possible to talk about, 10 to the minus 43 seconds. The temperature was 10 to 32 degrees, and the density downright indescribable. At that instant, there was only one universal force and one type of elementary particle. But it wouldn't last. At the end of this instant, gravity separates itself from the union. At 10 to the minus 35 seconds, the strong nuclear force exits the union as well, and this triggers inflation, the event where the universe instantaneously grew into size, from tinier than an atom to an unknown large size. This expansion and subsequent cooling down to 10 to 27 degrees allows 6 different types of quarks to form. At 10 to minus 12 seconds and 10 to 15 degrees, the weak force and electromagnetism separate, and we have the 4 independent forces we know today. At this point, all 6 types of leptons have formed, including the electron. At 10 to the minus 6 seconds, up and down quarks have formed protons and neutrons. All heavy quarks have decayed. All heavy leptons have decayed. All antimatter has disappeared. And by the time the universe is only 1 second old, protons and neutrons are already getting together to form the lightest atomic nuclei.
Wait! Can you slow down and try that again?
Sure, Diana. Can you tell me the difference between force and matter?
Well, sure. Matter is stuff that you can hold in your hand, or at least visualize holding in your hand. And a force is something that causes matter to move, change, or react, an action. Air is matter, even though you can't see it unless you're in Los Angeles.
Pretty good. Now, consider a piece of matter, and imagine taking it apart down to its basic constituents, the particles that make it up, down to the atoms, and further down to the protons, neutrons, and finally to the quarks and electrons. If our hands were small enough, we could hold them in our hands as well. So, these particles pass your hold-it-in-your-hand matter test and are declared matter. But at this level of tiny, things get a little fuzzy. Watch this.
As we take apart matter, down to the smallest scales, we must pass through levels of structure that are only possible because of forces that hold these structures together. The proton and electron, for example, are attracted to each other, and that force of attraction is what holds them together in the atom. But what is it really that causes this attraction? How does the electron know the proton is there? And what draws it towards the proton? How does the electron know not to be attracted to the neutron? The answer is that the electron and the proton each fill the space around them with countless millions of other tiny particles that have only the most ephemeral existence. Because it is electrically neutral, the neutron does not. These particles come into existence only briefly and are gone, only to be replaced by another one thrown out by the parent particle. On this scale, the tiny bit of energy that is needed for the existence can be created out of nothing. But they also must disappear in the briefest instant, because the energy used to create them can only exist for a very brief instant. You can imagine these virtual particles as balls tethered to the parent particle by a rubber band and snapping back to the parent when they disappear. If one or more of them should encroach upon the territory of a virtual particle tethered to another parent particle, they can get entwined and exchanged. Such an exchange is felt by the parent particle as a force.
These fields of virtual particles surrounding a parent particle are created in very specific patterns and fill the surrounding space in a well-defined way, and scientists cleverly call them fields. The virtual particles are called carriers or mediators of force.
Scientists recognize 4 distinct kinds of force fields, and they all work through the mechanisms described above. You are readily familiar with 2 of these forces: gravity and electromagnetism operate on a scale that we encounter in our everyday life. A third force causes quarks to stick together in protons and neutrons, and a residuum of this force causes protons and neutrons to stick together in the nucleus of atoms. This force is called the strong force, or sometimes the color force. The fourth force causes radioactivity and is called the weak force. The virtual particles that make up these fields and get exchanged in each force are called gauge bosons. And each of the 4 forces has its own gauge boson. Within limitations, energy and mass can be created out of the nothingness of space-time, but only for a very brief instant. And the more energy and mass these virtual particles have, the shorter must be the time that they can exist before snapping back to the parent. Lighter gauge bosons can exist for a longer time, and these in turn can get further from the parent before they must return. So the range of a force is directly related to the mass of its gauge boson. The photon is a gauge boson for the electromagnetic force, and the graviton is the gauge particle for gravity. Both of these particles are massless, and so the range of these 2 forces is unlimited. The strong force is much more complex. The charge property responsible for the force between quarks comes in 3 distinct states. Not just 2, like the positive and negative charge states in electromagnetism. So in a loose analogy to the 3 primary colors, red, green, and blue, the 3 kinds of charges in a strong force are usually referred to as color charge, and are designated red, green, and blue. Since the theory of electric charge is dubbed quantum electrodynamics, or QED, the name for quark theory has become quantum chromodynamics, or QCD. It is interesting to note that all observed particles are white. Color is never visible. And since the proton and its baryon cousins each have 3 quarks, the color possessed by the 3 quarks must be 1 each of red, green, and blue, which sum to white. And mesons are always a quark and an antiquark pair, containing colors of red, anti-red, or blue, anti-blue, or green, anti-green. also combinations that equal white. The strong force, of course, must have its own gauge boson, and it turns out that there are 8 of them. 8 different gluons that carry the color force. And unlike the other force carriers, gluons have a color property themselves, and therefore interact with each other. Every time 2 quarks interact and exchange a gluon, they swap colors. Also, because gluons are attracted to each other, it is possible to have a gluon collection, which is referred to as, what else, a glue ball. The interactions that result from the weak force are incredibly short-ranging. They are effective over a distance even smaller than a proton's diameter. And this accurately implies that the weak force gauge particles, called the W and the Z, are immensely heavy. Over distances small enough and at really high energies, the 4 forces are indistinguishable because their respective force particles are also indistinguishable. The Standard Model of Physics combines QCD with QED and the weak force theory. It states that there are 6 quarks and 6 leptons and 12 gauge bosons, as well as their antiparticles. But only the up and down quarks, the electron, and the lightest neutrino are populous today. In the Standard Model, the entire system of matter and forces, except gravity, is encapsulated in a few simple equations and is organized around one core principle, known as local gauge symmetry. Amazing.
Okay, now do you want to tell me what you told me before I told you to tell me slower?
Sure. Let's go back to the birth of the universe. Things are hot. Real hot. And things are happening fast. Real fast.
For the tiniest increment of time that is possible to talk about, 10 to the minus 43 seconds. The temperature was 10 to 32 degrees, and the density, downright indescribable. At that instant, there was only one universal force, and one type of elementary particle. But it wouldn't last. At the end of this instant, gravity separates itself from the union. At 10 to the minus 35 seconds, the strong nuclear force exits the union as well, and this triggers inflation, the event where the universe instantaneously grew into size, from tinier than an atom to an unknown large size. This expansion and subsequent cooling down to 10 to 27 degrees allows 6 different types of quarks to form. At 10 to minus 12 seconds and 10 to 15 degrees, the weak force and electromagnetism separate, and we have the 4 independent forces we know today. At this point, all 6 types of leptons have formed, including the electron. At 10 to the minus 6 seconds, up and down quarks have formed protons and neutrons. All heavy quarks have decayed. All heavy leptons have decayed. All antimatter has disappeared. And by the time the universe is only 1 second old, protons and neutrons are already getting together to form the lightest atomic nuclei.